Remember that example we had in the beginning of the module when we explained while looking at a newspaper site how the state of our browser changed when we clicked a link? Well, that link that is hypertext. Hypermedia is a generalization of this. It adds other types like music, images, etc. In case of APIs, typically also just hypertext, so links, it's this hypermedia that should be the engine of application state. In other words, hypermedia drives how to consume and use the API. It tells the consumer whether it can delete a resource, whether it's allowed to update it, how it can create it, or where it can find it. Let's again have a look at the response that includes that self link we talked about. There's more. There are links to create a course for an author here, and there's a link to get all the courses for the author. So, this is actually already Hate OS at work. These links drive the consumer of the API. This boils down to a self documenting API, and the documentation can then be used by the client applications to provide functionality to the user. It's not an easy constraint, but it offers some really interesting possibilities, like updating a business rule at API level, which the client can learn without having to change the client. That's a pretty cool thing to be able to do. Alright, so that first constraint was a pretty large one. But this is it for now for the uniform interface constraint and its subconstraints. Let's continue with the next one, the client server constraint. This is a very basic fundamental constraint. It enforces client server architecture, which in turn enforces separation of concerns. This essentially means client and server are completely separated. A client, which is the consumer of the API in our lingo, should not be concerned with how data is stored or how the representation is generated. That's completely transparent. In our examples, our client is Postman. We have nothing to do with programming that at all, and it does not know how the API was developed. A server, which is the API, should not be concerned with, for example, the user interface, the user state, or anything related to how the client is implemented. In other words, we can design our API without knowing anything about Postman. Allows the client and the server to evolve separately. The third constraint is statelessness. You might have guessed that one from the explanation of the acronym we just learned about. This means that the necessary state to handle every request is contained within the request itself. State is thus not kept on the server but on the client. And when a client requests a resource, that request contains all the information necessary to service the request. If you look back at one of our requests, that means that the combination of URI, headers, and body are sufficient for the API to fully handle the request. It's one of the constraints that ensures that RESTful APIs can scale so easily. As the state to handle the request is contained in the request itself, we don't have things like server level session state to keep in mind when scaling up. Up next, the layered system constraint. That's a pretty easy one actually. A REST-based solution can be comprised of multiple architectural layers. These layers can be modified, added, removed, can be physical or logical, but no one layer can directly access a layer that's beyond the next one. That also means that a client cannot tell whether it's directly connected to the final layer or to another intermediary along the way. REST restricts knowledge to a single layer, which is the outer-facing one. That reduces the overall system complexity. Then we have the cacheable constraint. This states that each response message must explicitly state if it can be cached or not. Let's send a request to get our authors. And let's have a look at the response headers. There's a cache control header here and other cache-related headers like etag, expires, last modified, and vary, so the constraint is adhered to. Like this, we can eliminate some client-server interaction and at the same time prevent clients from reusing out-of-date data. HTTP cache, which is sometimes called the holy grail of caching, together with etags, is the typical standard used in a REST architectural system. Lastly, there's the optional code on demand constraint. This constraint states that a server can extend or customize client functionality. For example, if your client is a web application, the server can transfer JavaScript code to the client to extend its functionality. As said, this one is optional and it typically applies to web applications, not so much to APIs. So, that's quite a lot of constraints to adhere to. But we cannot build a RESTful system without knowing what it is, of course. Don't worry if you don't immediately see how to implement support for all of these. We will come back to them when applicable. Not all of these constraints are straightforward to implement. And to be completely correct, an architecture that skips on one of the required constraints or weakens it is considered not conform to REST. Most APIs that we build today and that we tend to call RESTful between quotation marks, well, they are not really RESTful. But does that mean that they are all bad APIs? In my line of work, most APIs I see when working for clients don't adhere to all these constraints. HateOS is a pretty typical one to skip. Personally, I think that's a shame, but that does not mean that they're bad APIs. It does mean that you need to know the consequences of deviating from these constraints and understand the potential trade-offs, which is what this course will help you with. It might mean that those APIs will miss out on some features, and if you're really strict, it also means that they cannot be called RESTful. I won't get into that discussion here. There's a lot of proponents and things to say for adhering to all constraints, but there's also a lot of proponents of a more pragmatic approach. In any case, we will try to build an API that adheres to all of these, including HateOS. Next to that, we will end up with a Level 3 API. What's that about? Well, web APIs come in many different forms, and there's a model that describes the maturity of them. That's what that Level 3 is all about. The model is called the Richardson Maturity Model. Let's have a look at that next.